Sveiki visi, laba diena, susirinkę šiandieną į paskutinę mūsų paskaitų ciklo Miesto atsparumas paskaitą. Kaip matote, paskaita vyks anglų kalba. Ją skaitys profesorius mokslų daktaras iš Potsdamo universiteto Jürgenas Kropas. Paskaita Designing Cities for a Safe Climate. Visą šitą jums pristatys šiandienos moderatorius Donatas Baltrušaitis, architektas urbanistas iš Bauland. Kol kas tik tai noriu paminėti, kad esam labai dėkingi, jog Architektūros kokybės vystymo asociacijai padėjo viešinant ir publikuojant straipsnius partneris žurnalas Statyba architektūra, portalas sa.lt. Ir žinoma, nebūtų galima suorganizuoti tokių šaunių paskaitų su gerais labai lektoriais, jeigu nebūtų papildomo finansavimo, tai yra Lietuvos kultūros tarybos ir UAB ACO Nordic. Mes kiek plačiau kiekvienoje paskaitoje juos pristatinėjome ACO Nordic, tai yra produktai susijęs su lietaus nuvedimu ir gatvėse ir nuo pastatų, ir iš tikrųjų labai patikima produkcija, rekomenduoju. Ir žodį perduodu šiandienos mūsų moderatoriai Donatui Baltrušaičiui, kuris ir papasakos plačiau apie lektorių ir paskaitą. Ačiū Jums.
Ačiū labai, Aidai. So now we will continue in English. We will start the official, let's say, part where lecture will begin with our invited lecturer. But beforehand, really thank you very much to Aida Štelvienė and this wonderful lecture series, which provide very useful, insightful, and sometimes even provoking information and content that we can introduce into architectural work style, urban work style, and landscape. Everything is connected, and I think not many of us here lecture, especially from a climatologist. So hereby we welcome our today's lecturer, Professor Dr. Jürgeno P. I will make a short introduction. So as I mentioned, it's a great pleasure to introduce our speaker, Professor Dr. Jürgeno P. a distinguished expert at the intersection of climate impact research, urban transformation, and sustainable development. So about our lecturer, Dr. Krop currently serves as the deputy chair of the research domain Climate Resilience and head of the research area Urban Transformations at the renowned Potsdam Institute for Climate Impact Research. His academic leadership extends to the University of Potsdam, where he has been a professor of climate change and sustainable development in the Department of Environmental Sciences and Geography since 2009. So wide and long-lasting expertise is further leveraged through his role at the Bauhaus Earth, focusing on sustainable building and development. Dr. Krop holds a doctorate degree in theoretical physics from the University of Potsdam, underpinning his analytical rigor and multidisciplinary approach to complex environmental challenges. And today, the lecturer, as by his words, will try to reveal how cities can contribute to mitigating climate change while simultaneously adapting to the challenges it poses, with significant attention dedicated to the urban heat island effect. Of course, we know that it's already a scientific fact that our cities face urban heat islands, one of the most pressing urban challenges of modern cities. How the materials and properties of urban buildings affect temperature changes energy consumption, furthermore, quality of life, demonstrating how architectural and planning decisions influence the climate and people's daily lives directly. The presentation will closely intertwine climate science, urban planning, politics to find answers to the question of how to create cities that are safe to live in the face of the approaching climate reality. As the professor holistically views the future of cities, stressing that solutions must be complex, responsible, and based on science. So I am really waiting myself for the lecture, and enough of introduction. Let's go to the content and Dr. Jürgen Krop, welcome. The floor is yours, and you might start sharing the screen. You will have 1 hour and a half for the presentation, and then we will have a discussion with questions about your lecture. So,
all right. I hope you can hear me.
Yes,
and you
perfectly.
can see also my screen.
And we can see your screen.
All right, that's perfect. I have to readjust a few things here for 1 moment. No. Because I have the bar on the middle of the screen. Okay now. Okay, good. Yeah, so hello everyone, good morning to all of you. It's a pleasure for me to give the lecture to you and share some thoughts and ideas how we can develop forward in the global urbanization, because global urbanization is a very prominent effect, which of course is not affecting only Europe, excuse me, but also the in particular the entire world indeed, and mostly it will take place in the developing world. So before I go into the details related to construction, I like to thank Aida and also Donatos for the very kind words at the beginning. As I said, it's a really pleasure for me to give a talk to you. Yeah, and the next 60 to 90 minutes, I will show you some insights we have gathered from the perspective of climate science, but not only. Donatos mentioned it, so I am also one of the partners of Bauhaus Oes. This is a new company, a non-profit organization in Berlin, which we developed from the point of view that it is really needed to change the actual styles of construction, because cities are indeed affected by climate change because of, let's say, increasing temperatures. I will come back to this effect later. But cities are also one of the root causes of climate change. And how big this issue really is, I will show you in the next minutes. So, the first thing I would like to discuss with you have to do, of course, with climate change in general. So climate change is really threatening the urban life, in particular the life of the very young people and also the elderly people. This is something which we normally subsume under the topic of urban heat island. But urban heat island in principle is a very, let's say, a very short description for a lot of underlying effects which are indeed related to the city planning, but also to the use of different materials in the cities. When we look on climate change, and I have taken this slide from one of the last IPCC reports, we should be aware of the fact that, for the very high emission scenarios, most of the people who will be born around 2020 will really perceive or will experience the upcoming change. And if I look into the global mean temperature change, and I guess you all have also read it in newspapers, we have approached one of the binding agreed climate thresholds, namely the 1.5 target, which was agreed on the Paris conference some years ago, that we have approached this level already last year. So we are now in a range of 1.5 year. Let me make also a short definition. When it comes to climate, we normally average the weather conditions over a time horizon of 30 years. So that means, in other words, that we have now observed the 1.5 degree threshold in the last year. This does not mean that this will also progress in the future because of the fact that we are averaging things, but it is indeed a warning sign. And but apart from this, we can make somehow clear projections into the future, because we know the physics behind climate change, and therefore we can say that people who are now just born or 10 years old, so they will have to tackle with the problem. That means this is a long-lasting problem, which is also for one of the tasks for even the younger generations. So when we look on the global temperature, you see here the global average temperature increase from 1850 to 2024. And you see that we have transgressed the 1.5 Paris threshold in the last year. So we were in a range of 1.6 degrees. But this is not all. So when we look to Europe, then we can say that even in Europe, the temperature is rising much faster, so twice as fast as in the rest of the world. And in Europe, we are already in a range of plus 2.4 in comparison to the pre-industrial era. So this is definitely a warning sign. We all perceive the consequences. We have dry periods during summer. We have in some regions extreme rain. And this is actually something which creates a huge amount of costs indeed, because our societies have to cope for the consequences. And this limits at the end also the maneuverable space, let's say, for our country budgets indeed. Yeah? So the more we have to invest into protection and into adaptation, the less we can invest for other purposes. Yeah. Okay. Good. So the question is, what will happen in the future? So when you look back to the last climate conference, or the United Framework Convention CCC conference, which took place just a week ago in Belém in Brazil. So we could not be really optimistic. And the reason why this is the case, you see by this graph. What does this graph show you? It shows you the temperature change versus carbon dioxide concentration since 1850. And what you see here on this graph is the following. So from 1850 until 2015, we have measurements. You see it here by these blue dots and the red dots. And what you can observe here is a remarkable linearity between the emissions, so the the greenhouse gas content, in particular CO2 in our atmosphere, and the temperature increase. So from 1850, we had around 14 degrees as a global mean temperature. Now 2010, we were in a range of 14.5 degrees. And when we move into the future, the temperature is further increasing. So when you would 1 moment, I don't know, something is with it's not moving forward. 1 moment. Okay, so now we are in a range of an atmospheric content of 423 parts per million, so in 2024. And you see that the dots are moving upwards on this more or less straight line. And you can see in which direction we will move. And when we cannot really bend the curve down in the future, it is likely that we would approach a temperature increase of 3.8 degrees in 2100. I hope that we can avoid it because 3.8 degrees means even overland a temperature which is probably twice as high as the global mean. The reason, and this will take place mainly in the northern hemisphere, because we have a particular situation here. So we have not an Antarctic continent. We have Arctic sea ice cover here. The Arctic sea ice is melting very rapidly, and the incoming radiation is then absorbed by the water, by the Arctic Ocean. The Arctic Ocean is heating up. The Arctic winds are becoming warmer and warmer, and this also is increasing and accelerating the warming over the European hemisphere. And this is actually what we can observe already. Yeah, so the actual emissions in the moment are 39.6 gigatons per year, and we do not see really a signal, not in the moment at least, that we can bend down the curve. So this 1.5 target you may see here, so it means an additional 30 parts per million of CO2, which means in principle 240 gigatons of additional CO2 emission. And this level was estimated that we would approach this in 2030 or 2031. As I said, so we have transgressed it already, but only for 1 year. This is a warning signal, but not an average signal as we consider it in climate simulations. Good. So, and the 2-degree target we will probably transgress in 2045 if we do not change something. This means additionally an add-on of 100 parts per million, and additionally overall in total amounts 800 gigatons of CO2. Yeah. So the question is now, so what does it mean? So what imply all this development? In particular for Europe, it could even, and this sounds a little bit paradoxical, could even mean that we would face extreme cold winters, at least temporarily. This has to do with the Atlantic meridional overturning circulation. So you know all that that we have Atlantic streams and also Pacific streams as well, and also streams in the Indian Ocean. And these streams are responsible for heat content, or for the transport of heat content. And what we have in particular in the North Atlantic Ocean is a transport of very hot water from the Caribbean Sea to the north. This has a result that, for instance, the harbor of Tromsø, which is very far in the north of Norway, is all around the year ice-free. Yeah, we have a heat anomaly. So in the northern part of the Arctic, it is warmer than it should be when you, for instance, compare the latitude of, for instance, New York with a bigger city in Europe. Then you can immediately see that New York is on the same latitude as Rome, for instance. But we have never seen heavy winter storms as we can observe them year by year, for instance, as in New York. So this comes from the effect of the North Atlantic Gulf Stream. And now we have the problem that global warming is weakening this Atlantic conveyor belt. It is weakened first by the melting of the Greenland ice sheet. So because when fresh water flows into the North Atlantic Ocean, That's the first fact, and the second fact comes from the weakening of the cold Arctic winds. So that means the sea surface is heating up. This causes some impact on the conveyor belt and leads to a temporarily cooling down in the Arctic region. So this sounds paradoxical, but it is only relevant for a shorter time horizon, because overall once again, okay. Overall, the global warming will proceed. Yeah, what all this is also causing are extreme events, and these extreme events are threatening our infrastructure, in particular the infrastructure in our cities. And as you may see on the lower left, this is a graph from the last year, but also some measurements are indicated here, taking in this year, so on the 29th of June, for instance. And you see that 2024 and also 2025 was above the global mean temperature. It was in particular at the upper edge of all this ensemble which have been recorded during the past years. And what this indicates, you may see on the upper left side, namely, we increasingly see so-called atmospheric blockings. What are atmospheric blockings? I guess here in Middle Europe, we normally perceive a rapid shift of low pressure systems and high pressure systems from the west to the east. And these high pressure systems and low pressure systems are closely related to the jet stream. You see this red band here, this meandering band. This is moving permanently around the globe. And this is, of course, indicated by the Earth's move in general. And you all know the effect. So when you're flying from here to New York, you often need longer in comparison to the return flight from New York back to Europe. Normally, as I said, so this jet stream band is meandering around the globe with the permanent speed. But when the global mean temperature increases, then it slows down. And sometimes we have so-called persistent weather conditions. Persistent weather conditions are conditions which are long-lasting for, let's say, 1 week or 3 weeks or even a month. And when that means, in other words, a low pressure system or also a high pressure system remains over a particular area in Western or Eastern Europe. And this is what we have observed in the past many times. So the first event was the European heat wave in 2003, for example, which caused the death toll of 70,000 people, and so excess mortality. We have observed in 2010 an extreme heat over Russia with forest fires, as you may see them here. And in the same time, in another region, we had extreme floods in Pakistan, causing millions of people losing their shelters. In 2010, 2011, we had in Central Europe a heavy snowfall with particular consequences. And when you go into the literature, you see now that there are many other events which we can now assign to a blocked jet stream. So, and the heat transport in the atmosphere, of course, gives serious signals. So when you look into the weather conditions, for instance, in Spain, in El Granado, we have observed the highest ever measured temperature in June, namely 46 degrees. And also the February to April 2025 was the driest spring in Germany's ever measured since the beginning of the recording. And as I said already, so the mean temperature in Central Europe increased by 2.4 to 2.5 degrees since 1881. So this would mean, when it comes to heat, that we could observe all 2 years a heat wave. So that's a more or less worst case. A normal occurrence of a heat wave would be every 10 years. Yeah. So this is a development. And when you look now to the cities, you see the consequences. We did already a large number of simulations about urban climate development in 2015, 2017. And you see here that already today, let's say the mean temperature in bigger agglomerations is twice as high in comparison to the urban vicinity. So this is well known since years, and also the urban heat island effect is well known since years. Yeah, at least 30 years. But the question is, what happens when we cannot reduce carbon dioxide emission? And this is what you see here on the lower part of the image. You see that the number of heat days can even be increased by a factor of 10 in the worst case. And this would, of course, create a lot of problems, health problems in particular for elderly people. So in this, when we take this into account, of course, we have probably to rethink really urban planning. So we have to consider, for instance, spaces for the elderly and also for the younger people in urban areas where they can go when they are suffering from heat exhaustion, for instance. We did also a lot of work in terms of heat wave studies. So we analyzed across Europe more than 4,500 cities, and we went also in very much detail of urban planning and also the shape of urban systems. And what we could do, we could really find out that the urban form and heat island are closely related. So here you see a simulation study for the city of Berlin. So what we did here, so we created a constant weather situation, but then we varied the density, so the density of the built-up area, also the height of the buildings, the city size as such, and also the cluster distance. Of what means cluster distance. So we were considering, let's say, built-up clusters and the urban green in between. And what we find out is that if we use contemporary materials and also contemporary construction methods, then we can clearly say that polycentric systems are much better for heat mitigation, so loose structures, so to say. But this is somehow also a contradiction of the actual city planning at the moment, because we all know that urban land is rather costly, and that city planners all around the world have the idea to densify cities further. So it's also the case here. But when we know that building height and also the building volume would increase the urban heat island effect, and when then it's in principle a target conflict. Yeah? So what should we do? Should we densify cities further, so in order to avoid large costs, or should we create some loose structures on the price of, let's say, other land in the near vicinity of a city? So that's not a solution which is easy to decide. But nevertheless, these are the scientific facts. This is the point. This is how climate change probably could affect urban systems. So there are many other examples. A couple of years ago, we had extreme flood in southern Netherlands and western Germany, causing a death toll of more than 150 people within a few days. Of course, I could show you more shocking images here, but this will not really help us to look on the underlying problem. So as this flood took place in North Rhine-Westphalia, southern Netherlands and Belgium, we found at the end out that the warning signals were given by the German weather services just 48 hours in advance. and also by the European Weather Service, so Copernicus. So they all sent warning messages to the administrations, but the administrations were not responding on time, and this then at the end was causing this disaster. So that means it's not only planning; it is also something which is related, when we like to cope with the extreme events, something related or somehow related also to the institutions. So we have to make them also better in terms of response time, in terms of responsibilities and all this. So, but when we look at urban systems, we have also to state that our urban lifestyle is one of the root causes of climate change. And now you may ask me why. I collected a little bit of information which you may see here on this slide. What we have to say also, and this is rather relevant, so cities are producing 85% of the global GDP. So that means, in other words, cities are the centers of course, of creativity. Cities are attractors, so to say, of natural resources and also other resources. So even human resources. So globally, we see still the effect that people are migrating very, very fast into cities, in particular in the south. On the other hand, one could say, okay, is this really relevant? Because cities are occupying only 2 to 3% of the land. That's correct. But when we look in general on global city systems, they are consuming almost 75% of all resources. And what is more important here, when we are talking about climate change, cities are emitting at least 70% of the greenhouse gases and produce at least 50% of the waste. So this could lead us to the point that we would say, okay, cities are inefficient. And for this purpose, it's worth to look a little bit to that, what happens in Europe. This is a collection of different numbers, which I took from various reports. And here focusing already on the construction process and also to the building stock we have in cities. So in principle, we can say that 60% of all European offices are not used, even not during the regular working times. So this might be an effect of the COVID crisis. So a lot of people are nowadays working in home office, but nevertheless, so this is not all. Namely, that we could also say that 10 to 15% of materials is wasted during the construction process. So that means, in other words, we are not very efficient when it comes to construction. Also, this is changing somehow, but we still see this when we look in a detailed way on construction sites. So 10% of the emissions are from the raw materials, from the manufacturing of raw materials and converting them, for instance, into, let's say, concrete or into cement, whatever we can imagine here. Another aspect which is related to the lifestyle is that 50% of the European urban residents state that they are living in 2 big houses and 2 big flats. That's interesting, so because we all like it when we have a lot of space, but nowadays things are also changing somehow because big houses also need huge investments in energy, because you have to heat your flats, you have to heat your houses, and this becomes increasingly costly. What we also have when we look on the construction process is that in Europe, at least for 55% of the demolition materials goes on waste disposals, and this is rather bad. in particular when we discuss the climate crisis, because the actual infrastructure which we have in Europe, and not only in Europe, also in the world, contains large amounts of embedded energy, also large amounts of carbon dioxide emissions. So therefore, this make waste linearity of our construction process need to be changed. It doesn't make sense to demolish a building and drop it on a waste disposal. It's much better to renovate it. Yeah. The other part of the climate relevance of buildings is the energy. I mentioned it already. So approximately 28% of the global emissions are coming from the operations of buildings. Okay, let me then come also back to the city organization, because also city organization is important. So 2 to 5% of the GDP loss we observe year by year is caused by traffic jams. So that means, in other words, by an inefficient transport system. And the next point is also not wondering, 90% of the air pollution is rooted in mobility. And this is due to the reason that we are still relying mainly on combustion engines, although this is also so on a mobility system which is driven by combustion engines. This is also changing. So Norway, for instance, made a lot of progress into these regards. So Germany is also now implementing a strong electric mobility system, but this, of course, would need time. And then the last point is related to the waste. So I told you at the beginning that cities are attracting materials, human resources, and due to the fact that we have a concentration of companies and also manufacturing units in cities, we are converting these raw materials into goods. We are using these goods, and one day they are damaged or we cannot use them anymore, and then we drop it on waste disposals. And this is the so-called individual municipal waste. So 75% of this waste comes from individuals, so consumption patterns, so to say. That's the reason why I said at the beginning that cities are inefficient, but it is closely related to our own consumption style. Let us focus on urban development in the 20th and 21st century. So you see here the development from 1950 up to 2050, and it is closely related, of course, to the demographic development. So demographic development is very easy to calculate, because we know already how much people we have on the planet. We know how much childs are born per woman, and then therefore we can make and then we can, of course, consider also fertility rates, and therefore we can make also very easy calculations to which number the global population will increase. But when you look on the time horizons here, so from 1950 to 2050, the global population increased from 2.5 billion. So sorry, I didn't correct it. It's still here in German. So 2.5 billion up to 7.3 billion. And the urban share was in 1950 30%, and it increased up to 55% in 2015. And that means when you break it down to decades, that per decade, we needed new urban infrastructure for new urban residents, and for a number of 460 million people per decade, new urban infrastructure. When you look now forward until 2050, so the global population will increase further to 9.7 billion. And it is estimated that then 2/3 of the global population will live in urban system or urban agglomerations. So, but this means, so when this speed proceeds, that we then per decade need to construct new urban infrastructure for approximately 740 million people per decade. This is a huge challenge, and everyone can, of course, imagine that this might not work when we proceed with our contemporary construction style, so to say, and also the use of the traditional materials. The UNEP estimated that this comes together with approximately 2 to 4 billion new flats or family houses until 2050. And everyone could ask, of course, from where should all this material come from? No. Yeah. And I guess you all know that in most of the cases, so when we are doing construction, so we rely on the global cement industry. And let me say a few words about cement production. So globally, year by year, we are producing around 4.5 gigatons of cement. But the cement production is rather costly in terms of the needed energy. So how is cement produced? So in principle, we use calcium carbonate, which we put into rotary kilns. So we increase the temperature from up to 900 to 1,400 degrees. And in this process, one of the CO2 molecules is separated from the calcium carbonate, and this is released to the air. But that's not all, because we need also the process energy. When you just put it in a chemical equation, you see the effect here. So CO2, calcium carbonate plus energy is then burned to lime. So therefore we call it also lime burning. And that means at the end we create 560 grams of lime and 440 kilogram or 440 grams of CO2 per molecule or 1 kilogram of calcium carbonate. So what the product at the end is what we call Portland cement. This means each a ton of Portland cement at the end is responsible for 450 kilograms of CO2. When you go to concrete, the situation is a bit different, because concrete is a kind of a conglomerate of different material components. So you have one part of cement plus 4 parts of aggregates, namely sand and gravel. So 1 cubic meter of concrete has a weight of 2.6 tons. And then you have also to consider the steel armament. And when you take this into account, then 1 ton of concrete is responsible for 1/3 of CO2 emissions. If the concrete industry would be a state, then it would come on the 3rd place after the great emitters, so China, USA, and then on the 4th place we would have India. So that's an interesting aspect which we now have to take into account here. When it comes to the embedded emissions, so the emissions which are in the concrete materials, it is not only concrete, it's also bricks. Yeah, so brick burning needs also energy. Then we expect, when we don't change our construction styles, that this will increase further, while the operational emissions will decrease due to stricter regulations. So, resource exploitation. So the question is, what does all this cause? When we look on the materials, we can say that the global human-made mass, so and here the construction materials plays an important role, exceeds already all living biomass on the planet on a yearly basis. So by more than 10% dry mass. And it is obvious that we cannot proceed this, namely when we look into the regions where most of the resources are consumed, then we can say less than 20% of humanity actually consumes more than 80% of the resources. And that means, in other words, wealthy countries must either dematerialize the technical basis of their prosperity or increase the resource efficiency by a factor of 10. What does it mean in terms of building? So first we have to say that opus cementitium is a very old material. It was invented by the Romans some 2000 years ago, but the binder in the Roman cement was not lime, it was pozzolan. So this is the volcanic fly ash they took from Puzzoli and also from the Vesuvio. In principle, we can do it similar to them, but the question is really when we need 4.6 or 4.5 gigatons of cement year by year, whether we can take all the binder from volcanic ashes. So I have some doubt that this is really possible, but what we know from history, the Roman cement was quite good. You see here the example that the cupola of the Pantheon in Rome, that was made by this Roman cement. So looking on the contemporary material, 4.5 gigatons of cement year by year, this is also what I said, but this comes together with a demand of 40 gigatons of sand and gravel per year. This has led already in some regions of the entire planet of demolishing of ecosystems, in particular in Africa, but not only, also in Asia, and river estuaries, for instance. But that's not all. We need also 20% of the fresh water demand for our construction activities. So this all, again, gives us clear warning signs that we have to change our, that we have really to change our, construction styles. So what is the conclusion? Okay, it's quite clear. Modern urbanism creates a lot of problems. So we are releasing huge amounts of CO2 during the production process of CO2. We have also huge amounts of energy stored in the buildings, actually. And the question is how we can change it, or is there a chance to change it? But before we go into this aspect, I will show you a work which we just published some weeks ago, 3 weeks ago, I guess. So what we did is the following. So we looked on the past, what happened with the construction industry, and found out that in the past 3 decades, the carbon footprint of the construction increase of the construction activities doubled. And when we take into account the global growth, so the demographic growth, then and then assume that we apply a business as usual scenario, then the carbon footprint of the future construction activities will double again. And then we try to find out how this relates to the 1.5 degree thresholds and also to the 2 degree threshold. And we found out that the carbon footprint alone, when we don't change things, will really transgress the 1.5 and probably also the 2 degree thresholds alone. Yeah, so that means all the other aspects, so agriculture, transport, and so are not included here. And this is really a bad message. But what we also found out, we can in principle change it. We made also a comparison and found out that bio-based materials are by far not so carbon intensive as other traditional or contemporary materials. You see it here. So in 2025, more than 50% of the emissions came from traditional materials. This holds only for the construction sector, by the way. 37% of the emissions in the construction sector comes from transport, services, and machinery. and 6% only from the used bio-based materials. And that's interesting. And then we were thinking, okay, what to do in the future? Can we make use of bio-based materials? And yes, in principle we can, but the question is now how? What you see here are proposals made by many research groups in the past. So as we were agreeing on 1.5 and also on the 2 degrees threshold on the Paris conference, we were also immediately asked, okay, what kind of trajectory we have then to follow to bring us down to net zero in 2050, for example. And you see here the different trajectories. So the black line is that what we have observed or measured, and all these colored lines here are potential scenarios. And you see, the more we are emitting, the more demanding it would be to keep the world on a 1.5 pathway, for instance, because then the steepness of the bended down curve must be very high. So this is something what you see here, and what you also may see from this graph is that here the assumption is that we would have started immediately with a decrease of the carbon dioxide emissions. We all know from the measurement that this did not came true. What the scientific arena then did in addition is something what we called overshooting. So what means overshooting? Overshooting means, or from all the calculations which I have shown you before, we know how much emissions we can still emit to the atmosphere in order to keep us on a, let's say, safe level. So let's say below 2 degrees. But what we also found out in the scenario simulations is that we can, for a while, transgress this limit. But then we have to come back immediately below a particular emission level, so that we then can keep the world under this 2 degrees centigrade threshold. This you may see here. So we have assumed here the peaking in 2020. This is a little bit older graph, and then later we shifted it to 2050. And then you see again, so this is the business as usual scenario. Then we assumed that after 2050 we can bend down the curve. So in other words, that we are transforming our industries, that we are transforming our mobility system, that we are transforming our construction sector. This is then, or comes together with pledges which we did on all the conferences. So on the climate conferences, the countries were reporting to the United Nations Framework Convention on Climate Change how much emissions they would like to save. And this is what we call then avoided emissions. But as you see, there is still a gap between the avoided emissions on one hand, and of course, the remaining emissions. So we are not in the range of 2 degrees here. So we have remaining emissions. And the question is what to do with the remaining emissions. In other words, we have to invest some efforts in negative emissions. So what are the negative emissions? Negative emissions are in principle withdrawals from already released emissions. This is what you can do, of course, with technical solutions. So these are already available. Or you can do this by the use of nature. And this here the construction sector comes into play. So how we can constrain the consequences, how we can mitigate the further temperature increase, and which options do we have. Here you see again a little bit the graph, a bit more detailed in comparison to that what I have shown you before. So you see the thresholds here, 2 degrees and 1.5 degrees, and this is a measurement which goes up to 2020, so a stylized measurement, so in principle the mean. And when we proceed with our emissions, the next development will look like like this. So this is a business as usual scenario. So we will go up in a range of 4 degrees at least. But we can also try to create an overshoot point in 2100. So you see that with a particular emission amount, we would transgress 2 degrees, but then we will be able to bend down the curve again so that we then go down again below 2 degrees, what in principle would be a good solution. But here we have a big gap between the business as usual and the negative emissions, and this is actually what we call negative emissions, and the question is how to deal with this negative emissions. And here we like to make use of nature, namely by using timber as construction materials and also as a storage repository for emissions. But apart from this, we have also to think about postmodern cities, how they can look like, how we like to design it. And I spoke in the beginning of my talk already about greening cities. Here you see a very visionary idea of a city development, which is quite green. When you really want to make a city carbon neutral, not carbon negative, I would talk here about carbon neutrality, you have to rethink the narratives of urban life for the 21st century. So this is almost clear. You can mitigate the heat burden, as I have discussed it earlier, by creating an urban space which is only fairly connected. But this means that you would also have, let's say, a very efficient transport system, which is based on electricity, for instance. So in principle, we have to think about the reconfiguration of the co-evolution of human civilization and nature. So as I said, so polycentrism is much better instead of the well-known brutalism à la Le Corbusier. And indeed, it's useful to think about the use of biogenic material. You see an example here. So that's a multi-flat house. And in the remaining time of my talk, I will now discuss a little bit about the use of timber and what this means in terms of in terms of the sustainable use of timber resources. Yeah, how could modern cities look like? You see some photos from various places in our world. You see that cities are becoming more and more green. So this is actually also what the people like. They want to have their cities back. They don't like these traffic jams anymore and this air pollution. So this is a movement which you can observe all around the world. And in principle, it's good, but we have to do it in a soft way. So we have to consider a lot of different ideas here and also target conflicts, and this is something what is often not aware to the people. So they are overlooking only their, let's say, their own quarter, so to say, and want to apply a solution in their quarter without taking into account that this particular solution could also create negative effects in a neighboring quarter. So first of all, this is a German book, by the way, but I translated the title. The title is Prohibits Construction. So this is a very good idea in principle. I mentioned it earlier. So we should avoid demolishing. So existing infrastructure contains huge energy quantities and also embedded emissions. And I show you here an example. This is the administration of one of the Berlin zoos. It looked like this here on the upper right. It was a concrete building, and then colleagues from the Technical University in Berlin, so the Natural Building Lab, they did an assessment for the global warming potential for 3 cases. You see it here. So the green is means partial demolition and renovation. So you see here, this is global warming potential. It has a lowest impact than, of course, complete demolition and new construction. Has already a much bigger impact, and the complete demolition and the substitution, which is similar building, has the biggest impact. So this is something what you can apply to any of the buildings. Of course, it's a bit more costly, but it's worth to invest these costs, because overall, when you take into account also the environmental costs, things so the construction process is cheaper. So how it looks like today, you see here that this is a photo taken 2 years ago. That's a new administration. So the old building style was more or less kept, but what we see here, so the front and also main parts of the building are now equipped with timber fronts. This is a good idea, indeed. So, in other words, built by nature. So that is the idea. So we can probably accelerate the necessary transformation by substituting materials which are rich in carbon dioxide and store it and avoid it. And in parallel, we can even implement a new building culture. And this new building culture is not really so new to us because we have long-lasting, hundreds of year experience with this. But there are many studies out there which are also showing that the features of timber-based buildings are also remarkable, at least to some extent. So there is an interesting experiment which was done at the University of California in San Diego. So they built a 10-story mass timber building here, as you see it here. And they did it because of the fact they wanted to compare the seismic resilience of such a building. And what they did at the end, they made this building is on a shock plate, and then they increased the seismic energy of the shock plate up to a Richter scale of 6.7. So this is similar to that what happened in during the Northridge earthquake in 1994, and nothing happens. If you like to know more about it, you can go to the internet, to YouTube. There's a nice video showing you what these shocks are inducing in this particular building. So there is another interesting experiment which was undertaken by Chinese scientists. What they did, they built a replica of one of the buildings from the Forbidden City and increased the earthquake energy up to a Richter scale of 10.1, which is an earthquake which has been never observed actually on the entire planet, at least not in modern times, and nothing happened. And then they were looking why this is the case, and of course they found out that the ductability of the building, of the parts of the connections of the buildings, played an important role. The replica from the Forbidden City was based on very big timber beams, which are not permanently digged into the earth. So they were standing on a more or less variable on a concrete plate. So that gave the building the opportunity to move with the earthquake shocks. So this is an interesting aspect. What we also know is that timber buildings also can meet heat burden because timber has a lower thermal conductivity than other traditional materials. So the problem with the urban heat burden is that during the summertime, for instance, concrete absorbs the solar radiation, so the energy is then stored in the building material because concrete has a very high heat storage capacity. And when you have a series of consecutive heat days, then it happens that the heat is migrating through the building wall and one day you have the heat inside your house. And when this is the case, then it's more or less impossible to cool it down again. So it needs then again weeks before temperature goes back to the normal levels. I made this experience definitely in 2003. I couldn't live in my flat anymore, so I was sleeping during these heat waves on my balcony. It was absolutely incredible during these times. So another aspect which is often mentioned is related to the fire resistance. And we all know, unfortunately, since the 9/11 event, that of course concrete and timber frames are not so durable as we have expected. Yeah. So because, as you all know, after a little bit more than 1 hour, both World Trade Centers were collapsing because of the extreme heat inside of the building, which was caused by the fuel of the aircraft. When we compare this with the fire resistance of a timber building, so also a lot of experiments have been done here by the ATF in 2021, and they found out that 5-layered plywood cross-laminated timber building could withstand more than 3 hours, yeah, against the fire. The interesting thing is here that we would not avoid the burning of a building. So the issue of fire resistance is that we would give the residents a time to leave the building. This is the important point, yeah. And 3 hours is by far enough to leave the building under normal circumstances. Of course, you can always create situations in which this not might be possible, but nevertheless, it is absolutely comparable to traditional materials. And then the last, but from my perspective as a climate scientist, the most important aspect is related to the global warming potential. And here we have, of course, some studies which we can take into account, for which we have the material lists. So the material which has been used for the construction of the buildings. And one of these examples we analyzed in detail is the so-called Forte building, which was built in Melbourne. So they planned it twice, one time as a timber building, and then another time as a traditional concrete building. And because of the material list, we are now in the position that we can calculate the carbon storage. And also the absolute difference, because when you would do it in a traditional style, your building will also release emissions. And you see here the storage potential of this very small building was around 770 tons of CO2. And the absolute difference is 1,600 tons of CO2. So in other words, this means you can avoid and store 0.5 tons of CO2 per square meter. And this is really remarkable. And if you look into the details of other buildings, you see some similar numbers here. For this one here, so there's a Södra building, which is in Sweden, the Stora Enso in Austria, the Massivholz house in Austria, and then we have the Binderholz system in Germany. You see also that they even have higher numbers. We need to take them also somehow with care, because also the production of the materials which you can use in these kind of houses would cause some emissions. These you have also to take into account. I don't know exactly whether this was done here, but nevertheless, so we are coming to similar numbers. Yeah, okay. If this would be a solution, then we have to ask ourselves, do we have enough timber so that we really can equip the world with houses, yeah? Made from timber, just in order to mitigate the climate crisis and also to maintain or to keep forests on a sustainable level. And as you may see here, so this is the overshoot day in terms of the ecological footprint. So we are considering here the biological capacity of the entire Earth on an annual basis. And you see here when countries have been overshooting their own resources. And for Germany and Ireland here as an example, this happens already on the 2nd of May. So in other words, our biocapacity is completely consumed on the 2nd of May, year by year. So the numbers are not changing so much in comparison to 2025. It's almost the same. And by this graph, you can also see which countries are much better in terms of resource use in the moment. When we connect this to the use of timber resources, we need to be very concerned, because obviously this means that we are using too much resources and also too fast of our bio-based resources. And when it comes to timber, for instance, we can say that almost most of the timber resources we are utilizing in the European Union finally end up for energetic purposes. So in other words, we are burning them into bio-based power plants, for instance. This is somehow a bad development. So we here from PIC in particular, we have foreseen such a development, and we were warning against it, but nobody really at this time was listening to us. So using timber resources is not very valuable from the point of view of construction. It is also very valuable from the point of view of the bioeconomy, because we have lignite in timber resources, which is used by a large extent also in chemical processes. Okay, so the question remains, do we have enough timber? I did the calculations also by myself. This has been published in 2025 and as a book chapter, which comes on one of the next slides. So how much forest area or how much forest cover we do have on the planet? So this amounts up to a little bit more than 4 gigahectares, so 10^9 hectares. Totally. And actually, we have 45% of the whole forest cover on the entire Earth under management regimes. When we take this into account, so when we look on the managed forest, we then need to dive into details. So we have to consider the different management styles, and this is also what we did. We calculated then the theoretical timber yield by year. We reduced this yield down to 80%, because we were considering that not all of the timber amount which you can in principle yield in the forest could be really used or are also taken from the forest. So we leave also some materials there, and this is in principle quite good. And then we could estimate that around 4 cubic meters per year can be yielded from our managed forests on the planet. Then we also deduced the amount again because of production losses. So when we are producing timber materials, and we calculated the average CO2 content of 1 cubic meter of timber. So it's around 825 kilograms per cubic meter. When we look on the dry mass, and it's of course a little bit less. And we have to take into account also the conversion factor, so from C to CO2. Anyway, at the end, the CO2 fixation and storage is around 2.5 up to 10 power 12 kilograms of CO2 per year in buildings. And this is approximately 7% of the annual CO2 emissions. Okay, you might say that this is not much. Indeed, it is not. But it helps us already a little bit to bend down the emission curve. And what is more important, we really take CO2 from the atmosphere. When you do afforestation, for instance, so as we have it in the actual compensation schemes in the moment. Yeah? So when you are, let's say, using a lot of fossil fuels, you can buy emission certificates on the market, and with these certificates, and other companies are planting trees elsewhere, so mostly in the developing region. This is not changing the carbon dioxide content. It keeps it just on the same level because you're simply compensating. But when we are using timber, indeed, we are really taking emissions from the atmosphere. But the question really remains: could we really use forests in this way? And we have so there are also some studies out there dealing with forests and the use of forests, and what the colleagues found out, and I took here one of the quotations from New Zealand, because New Zealand is when in terms of geography and climate, and also in terms of plants and trees, forest cover, similar to that what we have in Northern and Central Europe. We can say that undisturbed forests do not accumulate carbon over time, because these forests are reaching a so-called equilibrium. We call it climax vegetation, here indicated by the green line. So only the young forests are really accumulating CO2. On the other hand, we have also the decomposition, so we call it here losses. And when you then combine this, you see here that we have at 430 cubic meters per hectare, we have an equilibrium. So this is a net change in stock. So in other words, managed when forests are managed sustainably, they can even provide more raw material. So carbon storage in forests is in principle finite due to the climate. And there are also other aspects, namely that we have forest damage, so it grows exponentially with the amount of above ground wood in the forest. So due to the losses, so due to decomposition, so we would have a higher risk for forest fires and all this. So in other words, when we manage our forests in a sustainable way, we can even gain more output. And this is not bad, indeed. Nobody really wants to transform the primary forest in the Amazon into a managed forest. So that's not the idea. So we're looking here only on those forests which are under management already. Apart from this, we can also look on the global tree restoration potential, although this is definitely, let's say, a prospective option for the next 30 years. But what we can say here, so we have 1 gigahectare of land available on the planet for afforestation. If we would do the afforestation on this area, we can also create a huge fixation capacity. Unfortunately, the political situation is not in a way that we can, or not framed in a way that we really could do that. We even have difficulties, as we also have learned from the COP conference in Belém, to protect the existing primary forests. Let me come back to the amount of timber we can gather from the managed forest. As I said, so I calculated, I did this idea in this book here. Unfortunately, it's only in German, but nevertheless, so maybe that we are still, and also it's available in French. This is also what I have to say. We are still working on an English version, but it's not yet out there. So if we take into account these three times 10 power 9 cubic meters of timber yield per year. Then we can estimate how much timber we would need for a family house, and then we can make the assumption that we would, that in such a house would live at least 3 people. So that means, in other words, we can create or can build approximately 2.3 dwelling 2.3 10 power 9 dwelling units until 2050. And this is in the same range of that what UNEP was demanding a couple of years ago. So in principle, we can follow this way, but we all know that there are a lot of hindering factors indeed. Yeah, I will come to an end with some examples. I guess, in your region, you have also good experiences in timber construction, but sometimes it's also worth to have a look on that, what is done. So first of all, I have to say that timber buildings have proven their durability and also their stability. So this is not really an issue anymore. Although when you talk to politicians, sometimes you could get a different opinion on this. So this is the Horyu Temple in Japan, which was built 710. So some of the individual components date back to even 594. So we could find it out via dendrochronology. So it's a very old building, but it's still there. The oldest building in Europe is a barn, a wheat barn, which was built in 1205 by the Order of the Knights of the Templar. It's in UK. And today we are doing it in a much more modern way. You may see it here. So this is Haus Köris or Building Köris. It is located in the east of Berlin, not far away from our place here where I'm in the moment. It was done by architects. So architects did this building, and it's based on prefabricated panels. So they have implemented also a roof greening, which cools down the building. And then we have an example here from Austria. So this is also a family house. It is, it contains also a heat pump and photovoltaics on the rooftops. And a very modern one is here, this multi-flat house in Kamen. So that's in North Rhine-Westphalia in Germany. It doesn't look like a timber building, right? But it is. So you see the energy demand. So the final energy demand, it's just 12 kilowatt hours per square meter in year. It's more or less nothing. Yeah. So this is it's a kind of a combined building. It's called Solar Building Kamen. It contains 30 flats. And it has also a heat pump for the heating system, and also an ice storage cellar in the below ground facilities. So this is something what you can do, and you can also move forward. There are other examples. We have also good contacts to Shigeru Ban. So Shigeru Ban is a Japanese architect, Pritzker Prize awardee. He is known for his very futuristic design things, so which he also applied to a lot of buildings. Here, for instance, this is the Centre des Pompidou in Metz in France. I was also involved a couple of years ago into training of architects, and this I did at one of the biggest brick producer in Germany. The company is called Hagemeister in Nottuln, and they developed. So first of all, they reduced also the carbon footprint for the brick burning. That was the first thing they applied, and then they combined together with the company which was also founded here in Germany, Trick Brick. They combined these bricks with calamity timber. So because in Germany in the moment, or in Central Europe in general, because of the heat summers, we have a lot of amount of calamity timber in the moment, and most of the forest owners say, okay, we cannot sell it on the market, we can just burn it. And the strict big company, so they developed a kind of a Lego style system, as you may see here, yeah. And then you can put the pieces together and then equip it with a brick wall in front of it, and then it works for buildings. I was also one day at the company Ter Halle in Ahaus, which is also nearby the Dutch border. So they built a whole quarter in the northeastern part of Berlin, so Kokoni 1. This is the quarter comprising many family houses, and they were producing everything, prefabricating everything in their company. Here you see this is the roof, and on the roofs you have also a photoactive tiles. So that means, in other words, your roof is also producing electricity. When it comes to the bathrooms, they have also prefabricated solutions. You can then decide how big your bathroom really should be. Would you work with a shower? Would you like to have a bathtub? Or would you have I don't know, a bidet, and then also, yeah, whatever you like. So you can decide it. So they have a series of solutions. Then you can decide, and they will drop it in. It's also prefabricated. So when the building is ready, then they put it on the train. They transported it to Berlin, and they told me within a week they have built it up, and a week later you can move in. This is rather fast in comparison to that what we did in the past, isn't it? And finally here, this is the ancient Milwaukee building. It has 25 floors, an altitude of 90 meters. It was finished in 2025. It has more or less the same height as a building which is in Norway, so the Miestų Tower. It has also, I guess it has a height of 89 meters. And the Miestų Tower is completely fabricated from timber, so even the elevator shafts are done by timber. Here we have a hybrid building because we have the ground floor which is made from concrete, but overall this building is also a timber building. The interesting story is, although the Americans have a good experience with timber buildings, so when you travel through the US you can find many of them, only small ones, but nevertheless, the interesting thing is that this building was prefabricated in Austria and then transported to the US. Yeah. Then some other examples here from Germany, because I did a speech that on an event just a year ago. So that was a prize for timber construction in the state of Lower Saxony of Germany. Here 2 examples, very big examples. So this is Sartorius. It's a company, and they did a research building in Göttingen, nearby the University of Göttingen. It has a size of 30,000 square meters. This is one of the largest timber buildings in Germany. It contains 260 working places, laboratories, and also technical offices. And again, when you look from outside on these buildings, you have the feeling that this is not really a timber building, but it is. Yeah. And then another interesting exercise which was done in northern Germany, in Lüneburg. So this is a kind of a community housing project. So some people joined in a kind of an association. They wanted to build a sustainable house, and they applied many different construction technologies to it. They used bio-based materials like straw, clay, lime, and wood. And their challenge was in particular the combination of all these materials, because the material classes indeed differs fundamentally from, at least from conventional construction methods, but even when you want to combine them all. But this is a final building here, and you see also how it looks like now inside. But during the construction process, you may see here, so what they did in terms of straw walls. And the interesting thing, and I will come to an end now, is that this is not really a new technology. You may know Albert Einstein. Albert Einstein was a famous German scientist, and not far from here in Potsdam, he had his summer house. And this summer house was built by a German architect, also by a Jewish architect who also migrated then to the US, Konrad Wachsmann. And he did this building as a timber house. And when you go to so you can go to it, it's just 9 kilometers from the place where I am in the moment. When you go to this place, you can also have a look into the history of the building. And when you look to the walls, they also were applying straw to the walls. That's interesting. Yeah? So it's not really new, but we have indeed to reconsider what we did already in the past. So back into the future. So we have to think about new materials based on, on that what we know already. So we have alternatives, not only timber. We can use hemp concrete. We can use natural stone. We can even use bamboo. So we have some projects together with partners in Asia. So they are using bamboo material for construction purposes. So this is something what we have to take into account, use the material where it is available, change probably the building codes, because we have a lot of bureaucratic regulations in our construction regulations. So this needed to be changed. And politicians, at least on the European level and also in Germany, they're working on it. And when we, of course, use forests for construction, indeed, we have to do it in a sustainable way. That means, in other words, we have to insist on strict certification mechanisms. We need to know from where the forest resources are coming from. Otherwise, we would create a tremendous threat to our global forest resources, and this is something what we really should avoid. Yeah, and when we look back to the technological development, so of course we are always focusing on high tech or on no tech solutions, but in principle we should find a way which we could call middle tech. So what means middle tech? We have learned so much from the past during the centuries, and it's nowadays we have the opportunity to work with digital twins. Of course, we have very good machineries we can use for prefabrication of modules, and this is all what we can apply now to the construction process in order to make it better, in order to reduce the carbon footprint of the construction industry. So in other words, we should try to bring all these things together. So no tech meets high tech in this way, and we need also for the building sector a smart circular bioeconomy, which is probably competing with other industry branches about the resources, but this to some extent is normal, and which could create further technological innovations. Okay, what this also could mean here, this is a pavilion which was 2019 built in Heilbronn in Germany, in southern Germany. It was used on an exhibition, and in 2023 this pavilion was then moved to the city of Mannheim. So that means sometimes you can even move whole buildings from one place to another. So the Swedish guys also made a good experience with this. I just noticed that in Kiruna, this city where they are digging the iron ores out of the ground, they moved one of the timber churches from one place to another. So this is much more possible than for concrete buildings. But what all would imply this is the following. So we should always, when we start with the construction process, with the systematic analysis of the value change and also with the global warming potential. And here we have to valorize the building materials from an economic and also from an ecological and also socio-ecological perspective. And then, of course, we can implement a circular economy much better than relying on the so-called linear value change, namely the take, make, dispose economy. Of course, we still have many things to solve, because when you take material from renovated buildings or demolished buildings, it's not so easy to reuse them. But here we can also think about particular certification mechanisms, and we can also use blockchain, for instance, as a let's say as a kind of a material passport, so that you can really look back where this, let's say, timber beam or even concrete beam has been used before in a building and what their technical features are. So this is something what is in the discussion in the moment. Okay. I guess this is my last slide, yeah, so we should also come to an end, because I have also later to teach. And with this, I'd like to thank you for listening, and yeah, thank you very much.
Thank you so much, Jürgen. It was really inspiring presentation. Me personally, I really liked how you came from a worldwide perspective, really pinpointing the key challenges of climate crisis that is happening right now, while at the same time you managed very fluently, like, let's say, to zoom in to actual possible solutions, so we wouldn't feel too overwhelmed, and maybe that we would feel that there are certain solutions possible to help to deal with these ongoing challenges. I would like to ask you, how many minutes exactly do you still have for our discussion?
Yeah, 10 minutes probably.
10 minutes, okay. So maybe we will have a question or two from the audience, but before that, I have a couple of questions also that maybe you could try to answer or comment. It is also a really interesting remark of going back to the future, as for example, Vilnius, our capital, for example, until the 17th century was mostly built out of wooden houses until medieval times. However, during the history of Vilnius, severe fires sometimes burned up to 90% of the housing stock. So slowly after that, the city has reoriented itself to brick building. And we are still really afraid, I think, in our subconscious to build from wood because of the fire threats and the past history. And then again, there are regulations, economic costs, and so on. But but we could also be happy that that some action is being made, that new public buildings in Lithuania are required to use at least 50% of wood or other organic building products since last few years. But I don't know, what would you say for the people who are afraid of using timber? Because as you mentioned, with the fire, that it's a few hours is enough for evacuation, and timber can have great fire resistant qualities as well. How is it in Germany?
Yeah, it is always an issue, but nevertheless, so these experiments shows you that this is not really a risk. So because the relevant time to cope with fire risk is the evacuation time, and when you're looking when you're using these very big timber beams, let's say as a skeleton of the building, then it's not really the problem. In terms of family houses, the situation is a little bit different. But for family houses, we have weaker regulations. It holds also for traditional family houses, indeed, and the highest fire risk for houses you have indeed inside. So because your furniture, your carpets, and so they are very, very dry. So that means, in other words, so when you have really a fire, most of the fire outbreaks are coming from inside of a flat or inside from a house. And this is due to the fact that you have that you are accumulating a lot of material which you can easily burn. Yeah, so it's mostly an issue of that you're not be careful with the use of open fire inside of your flat. So when you look back to ancient times, so let's say the big Roman fire, or also the fire which we had in London in 1400 something.
Yes.
So these are fires which were caused by also an uncommon use of open fireplaces in the houses. And then, of course, at this time they didn't invested so much efforts in the planning of the building. So they were very, very near. So the streets were very narrow. So that meant, in other words, when the fire started in one building, it could easily move to the next building. This is not something what we would do today. Yeah.
Yeah, well, I think it really answers that we already moved further with
We are
our
moving forward.
technology and regulations to avoid this. Then another one, when I was listening to the lecture, I was thinking that, well, Lithuania is really rich with forests, around 35% of all land. However, there is a huge ongoing debate on how much we can cut, how we should cut, reflecting to biodiversity reasons, the loss of biodiversity, and especially oldest forests overall. And so this might be really a sensitive issue if we are to reorient the whole construction sector in the future for timber-based construction. What would be your comments on that?
So it's always a compromise between let's say keeping forest as natural assets. On one hand, this is a good idea indeed, because it creates also a safe environment, and we all like it when we can go to the forest and so on. On the other hand, these natural resources we can indeed use. It does not mean that you should use everything. You should also keep the primary forests because of biodiversity. This is very, very important also in regard to climate protection. But I have shown you that that managed forests can even accumulate more CO2, and this is a real asset. But in any country, so when we are using the resources, we should be very careful in doing this. Yeah? So we need clear regulations so that we not come to a pathway of exploitation. This would be rather bad. And this is, so sometimes globally we see a lot of hindering factors. The WWF, for instance, they are saying, okay, we are using already too much of the forests, and we are decreasing global biodiversity. All this is true, definitely. But I understand my talk also a little bit as a talk which could create a vision for the future, because just to say we should not use our forests because of the climate protection, this is not sufficient. So when you're in parallel, you are digging tons of and gigatons of sand and gravel out of the earth. Yeah.
Mm.
So this is, I know that it is difficult.
Then again, for example, our forests are almost half of them are made of Scots pine, and which is not really durable and long-lasting building construction. So even when we do landscape projects, for example, and we want durable, let's say, wood, we're still looking for stronger wood outside of Lithuania, and maybe sometimes even imports from Africa, which also is that, you know, this is another crazy moment that you try to use wood, but then, like, for example, that modules made in Austria, and then the building stands in the US. But yeah, I see that Aida has raised her hand, maybe a question.
Yeah. Just like a continuation, I wonder, concerning Jürgen, your calculations, you mentioned that 85% of forest, manageable forest,
45.
45 even. Yes, 45. But still, for example, there was a documentary on Estonian case when the number of this manageable forest decreased very fast. What they changed, they changed regulation, what kind of forest hold that name. I mean that trees with 1.5 meters high, it's already called a forest. And we all understand that it's far years and years to become it a real forest. So maybe your calculation would change if you include this age statistics.
Yeah, this is what you always have to do. So you have to consider age. So we call it turnaround time. Yeah, so it doesn't. So you can. So an oak tree in Central Europe could have an age of 120 years or even older, but on this age, the tree is already in the climax vegetation. So it is losing material, of course. So it's decomposed while in parallel slightly growing further and further. But the uptake of CO2 is more or less constant. So it doesn't. So there is no increase. Yielding timber from managed forests means that the turnaround time of certain kind of tree species should be around 30 years, depending a little bit on the kind of trees, right? This is, otherwise it doesn't make sense. On the other hand, what I said, okay, so nobody is really or could have interest in cutting down the Amazon forest and also other primary forests around the world. So this is not what we really should do. But for the timber resources from different countries, we have to find out how we can really certify them. So in the sense that they're, sustainably yielded. So I was 3 weeks in Nepal just some weeks ago, and I was also discussing the issue with partners there, and they said, okay, so in Nepal we had an overexploitation of our timber resources, bringing us down to 10% forest cover some decades ago, and then they stopped everything. It is still not allowed to cut a tree in Nepal. They are now back to a forest cover of around 25% something. But they are not allowed to use the resources. So what happens now there is that they need to import timber resources from Indonesia. So, and as we all know, Indonesia is also a hotspot of deforestation and biodiversity losses. So that means, in other words, we have not really understood that we are living on one planet. Yeah, so it doesn't make sense to implement very strict regulations in one place while in other ones we do not have any of them. Yeah, so this is something what we have really to take into account here.
Complex problems should be complex solutions. And No.
There are no simple solutions.
Yes.
Mhm.
Okay, so I see that your time is finished. I have one final question, very short. What about glass in buildings?
Oh,
Architects
yeah,
love
yeah,
it.
yeah.
How is it with carbon footprint?
Yeah, the glass footprint is indeed also quite bad, indeed. Yeah, so because you need a lot of energy. The other point is that you can glass recycle quite easily. Yeah,
Mhm.
so because the energy is already in, so that's the reason why I said, okay, we need a kind of a circularity of implemented circularity for all the materials we are using in the construction process, including glass, indeed. Glass has advantages and disadvantages, so would be another lecture.
Yes, I can imagine.
But nevertheless, yeah, so it is not only glass, it's also alumina, it is plastics, and all these materials we need to take into account as well, indeed. Yeah.
Okay, so we don't want to steal more of your time. Thank you so much for all your knowledge, all your sharing. Keep
It was
up
a pleasure.
the magnificent work that you're doing, and comments are giving a thank you for the global view, Mr. Rob.